All right.
All right. So,
Go then.
okay, over to you, Randy.
All right. Okay, so let me share my screen here. Okay. All right, so I'm going to give a little update on boats. As per usual, all comments, feedback is welcome at any time. Don't hold back. So the first one is just a little reminder of some videos. Sorry, some videos that have appeared over the last year. So just remind people of some of the great vehicles people are building. So this is two videos. One of them was the these are both from RC Test Flight. Let me just go back a bit again. Try again. Remember this one, the banana slug, which is a little hand-built boat. Does a really long distance mission. It's over 20 kilometers, I believe. And then the next one that you might remember is RT Test Flight's solar boat. This is moving quickly, which again is very inspirational. This is another example from Andrew RW, who put a lot of effort into these autonomous buoys, and you'll see there's a long discussion on the in the forums where he details how he built them, etc. This is the boogie board boat from Chris Dalke, I believe. And this frame is amazing. So many people have built boogie board boats. It's incredibly popular. Next video is another autonomous buoy. This one from David Bullinger. Uses it for his local sailing club. And yet another autonomous buoy, this time from Roberto Navoni from LaserNav, who's been with the team for a long time. It's the important thing in this video is not the boat sailing around, it's the quite large red inflatable and autonomous buoy that he's using. This is John Easton's mapping boat. This is his new version called the Amy 2. And it's gas powered. And it's part of his business actually of providing detailed maps to fishermen. This was another famous video from Mike Holden. This is his autonomous sailboat sailing around the very large sail drone, autonomous drone boat. So only one of these boats has hardly piloted it. This is the somewhat famous Razor and CleanBot autonomous boat for cleaning up garbage in a harbor. Oops, sorry about that. See if we can get back to where we were. Skip forward here a little bit somehow. You just get to see them all again. Sorry, I'm not sure how to. I guess we get to see them all again. Maybe multiple times.
Try right arrow.
Oh, there we go. Nope, nope. Oh man, how many times can you see this video? So one more time, Andrew W's buoy boats, Chris Delkay's boogie board boat, David Bullinger's autonomous buoys, Roberto Navoni's autonomous buoys. A lot of autonomous buoys. I actually left out some autonomous buoy videos, if you can believe it. Yeah, so now John Easton's gas-powered mapping boat. Like Holden's autonomous sailboat. the Razor Clearbot trash collecting boat. And last but not least is my mapping boat. This was made in conjunction with a company called Lighthouse and also Shimano University. And that's it. So there's just one extra video at the end. Okay, so yeah, I just wanted to give it next a little bit of background on boats and why they're important and why there's so much interest in boats. So, you know, one of the things is that a bit like flying drones, boats allow you to go where you can't, allow people to go where they can't easily go themselves. Also, you know, we spend all our time on land, but as everybody knows, you know, 70% of the earth is water. And it's mostly empty, which actually makes it easy for us because unlike you know, rovers, which tend to be rolling around in close proximity to, you know, people and objects, you know, boats don't have to worry so much about that. The object avoidance is not such a big problem. You know, compared to copters, the vehicle's weight doesn't matter much. It's got the water holding it up, so you can go very long distances. You know, my mapping boat, for example, can do 70 kilometers, you know, even with, and it could go further if I just put more batteries in it. One interesting thing about the range, though, is that it can do very long range at low speeds because at low speeds, the efficiency is really high, but the range and the power consumption just drops off a cliff as you get to higher speeds. It's not at all linear. So, for example, my mapping boat can do 70 kilometers at 1.5 meters per second. But if you try to go 3 meters per second, you know, double the speed, and it goes slightly less than 20 kilometers. I think, you know, the next 2 points are just about sort of the market opportunities. There are, of course, lots of autonomous boats out there, but they're generally closed source and very expensive. It's a bit like the early days of drones, you know, where you could have a quadcopter that would cost $80,000. You know, autonomous boats, you know, you can have a 2-meter boat and they can very easily cost $70,000 or $80,000. So there's a lot of opportunity for, you know, autopilot-based boats, which can be much less expensive because, of course, you don't have to pay for the software development. You know, also the next is just that the manned boats are a huge business. We think about fishing and shipping, et cetera. There's a lot of opportunities there for autonomous boats to replace some of those manned boats. And so, you know, some possible applications, ways that we see people using autopilot drone boats and other boats. There's, of course, amusement and entertainment. So those autonomous buoys are definitely, you know, finding a real place out there. Of course, there's racing as well. There's photography, videography. The next big application is mapping. So like John Easton has a whole business set up around mapping, and there are lots of other businesses out there who do mapping as a job, as a business. And the reason is that amazingly, only 21% of the seafloors has been mapped. You can have a look at that link to Seabed 2030, which talks about it. But there's vast areas of the sea that haven't been mapped. And next one is delivery. We don't see too many autonomous boats being used for delivery yet, but we have had a couple of inquiries from like India and maybe Indonesia. So there's opportunities there. Next is surveillance and monitoring. So, you know, there's a lot of, not exactly conflict, but there's always, you know, issues around, you know, fishing rights and you know, who's allowed to fish here or go there, et cetera. So, you know, drone boats could be used for surveillance and monitoring to make sure that everybody follows the rules. You know, next one is something that I'm involved in, which is environmental monitoring and cleanup. So I work with some universities, and you know, my drone boat is useful for this. So, for example, one of the great things about drone boats is that unlike manned boats, it's very easy for them to go to exactly the same place, you know, taking exactly the same route many times. So that's very good for environmental monitoring, because you can go back to the same place and collect data in exactly the same way, and then you can compare it over time to see if the environment is changing or not. One of the last point is just around the opportunities to combine drone boats with submarines. So submarines are fantastic in lots of ways, but they have this big issue in that they can't normally use a regular GPS. And so there are underwater GPSs which are available. So I've seen multiple projects being proposed where some of these underwater GPSs are connected to drone boats or manned boats. And then, the submarine can figure out where it is in relation to those drone boats. So that's another opportunity, which is definitely out there. Any questions, comments? Okay, moving right along. So this is just about some of the recent progress, or the progress of the last year, I guess, for boats. So in the driver's area, we've added and improved the BL heli and D-shot support. So that's mostly Andy Piper. We've added solar panel controllers. This is Tom Pittenger. And I've put this on my boat, although it's not in the most recent video. We've added support for the torpedo motors. And the important thing about this is that it allows the boats to travel much more quickly. So previously, most of our users were using DC trolling motors or gas motors, gas engines, I guess. But we've added support for the torpedo motors now, which are electric and provide tons of feedback, but also they allow the boat to travel at more like 3.5 meters per second. Peter Hall added AIS support. So this is the boat equivalent of ADSB. So you can see where manned boats are. A bit like ADSB though, the number of boats that actually have AIS transmitters attached is quite limited. But I was lucky enough recently to do a big mapping mission out in Shimane in northern Japan, and a couple of large ferries floated by, and I was able to capture them and see where they were with the AIS support that we've added. Next is the Extreme ArduPilot project, which Tridge mentions in his slides. So this allows boats to go really long distances. So I'm really looking forward to the day when somebody has an ArduPilot powered boat, traveling across the Pacific or the Atlantic or some other large body of water. Small thing, we've added this misdone behavior. So this means that when the boat finishes mission, it can switch into loiter mode. Previously, it was just always hold mode, and then it would drift away. Small thing, but important. We've added support for Lua scripts to be executed within missions using the nav script time mission command. So that's great for adding custom behavior to your missions. Next is in the navigation area, we've added SCurves and position controller navigation to replace the old L1 controller. And I'll talk about this in more detail in the next couple of slides. We've improved the vectored thrust support. So vectored thrust is, of course, when you have an electric motor and it's being aimed by a servo. We've improved that support so that it more accurately gives you the thrust and turn rate that you want. Then we've done a bunch of bug fixes. So Peter Hall did a fix recently to sailboats loiter feature. So when it handles heading into the wind properly. Also, we fixed up a bunch of small bugs in how we were handling motors hitting their limits. So make sure now that that we don't get high turn buildup in the speed controller, which could lead to bad behavior during missions in particular. And Peter Hall also did a fix recently, I think, to the Omni boat support. So Omni boats, I'm sure everybody knows, but Omni boats have not just one motor, not two motors, but 3 or 4 motors. So it handles one of the motors hitting its limits slightly better. Any questions? No? Okay, moving on. So perhaps the biggest change that's gone in, and it's gone in quite recently, is the adoption of SCurves in Rover. And this took many months to get done, but hopefully it's worth it. Now, this is not included in 4.2, and I think that was definitely the right choice. It's sitting in master, and it's going to sit there, getting more testing until 4.3 goes out. Anyway, it's quite a big change, so I just wanted to try and familiarize everybody with how it works. So previously, the Rover software is a descendant of the Plane software. So it has been using the L1 controller, and that was working okay. But the L1 controller has, at least as it was implemented in Rover, had some limitations. So perhaps the two big limitations are, well, the first one is that it would only ever look at a single segment at a time. It did not do any forward planning. So, if the boat was traveling between, along this segment here, it would only look at the origin and the destination. It would not look at the next destination. So this meant that, as the vehicle, basically normally, the vehicle would reach the destination, it would then forget about the previous segment, and it would immediately move on to the next segment. The vehicle would overshoot the corner, which is okay for some applications, good for some applications, not good for other applications, but in any case, it would overshoot the destination, and then it would get a massive lateral acceleration request coming out of the L1 controller to get it back onto the path. So that was one limitation of the L1. The other issue is that the L1 controller is really just a lateral acceleration controller. It just tries to get to the vehicle. It just tries to provide a lateral acceleration to get the vehicle back onto the path. It does not try to provide a speed. So it just uses the current speed. So basically, the L1 controller and the speed controller were very separate, and that meant that we had to add in all kinds of little band-aids here and there to make the two of them work well together. So, for example, as the vehicle approached the destination, it would slow down. And then another one was we used to have the lane-based speed control. So if the vehicle, for some reason, ended up drifting too far off the path, it would just slow down the desired speed in the hopes that that would give the L1 controller a chance to get the vehicle back onto the line. So we had those kind of band-aids in place, and those are all gone now. Now we just have SCurves in the position controller. So is that okay? Yeah.
You had mentioned, Randy, yeah, this is Tom Pittenger question.
Yeah.
On you mentioned that this came, that they use the L1, which came from Plane. Is there any talk of moving SCurves to Plane?
Well, that's of course up to Tridge and the other Plane developers, maybe you as well. I was thinking that there are some problems. Is Leonard here? I'm sure Leonard will be here. I also had this in mind because planes and rovers are perhaps closer than copters and planes. So I thought the rover implementation might be a good test run to see if it was appropriate for planes. I think there will be some problems. SCurves have this assumption, at least at the moment, that when you hit your maximum acceleration, like you can configure the maximum acceleration that the SCurve path will reach. And if it looks like it's going to go over that, then it will reduce the speed. And but it will reduce that speed right down to zero, which is obviously not something that planes can physically do. So I think it's a good test case, but I'm sure that SCurves would need to be modified for plane.
I think this is Bill Geyer. I think if we were able to implement airspeed into copter for the navigation, that would be a good test case, because obviously airspeed is a big player for airplanes, and so I think that would be a good test case for how well it would work with planes.
Cool.
And of course, trying to keep the constant speed so that it doesn't go below stall speed or some sort of minimum speed.
Yeah.
If we were going to add it, I think probably we'd make it optional, at least in the beginning, and mostly because it isn't really something that people have been asking for. Whereas there were significant navigation problems that rover users were really hitting that I think which drove you towards put this effort in. And we're not really seeing that on fixed wings for the way people are using fixed wings. And so it would be quite nice to have it as an option and see how people found it. We have had done in the past. The original fixed wing controller was a vector field controller, and then we switched to the L1. We actually had both of them in for a couple of releases, and then we had a parameter to switch which one you want to use. So we'd probably do something like that, and then see how it goes in Rover, and then maybe have it as an option, and then see how well it works.
Yeah. Okay. Any other questions, comments? All right. So, okay, I'll go into now the details of how we've implemented SCurves and the position controller. So there really are two parts to it, two sort of separate parts to it. The SCurves are there to calculate the path. So we pass in now obviously the origin, the destination, and the next destination to the SCurves. It actually comes up with two separate SCurves, and then we blend them together. But that's all kind of hidden away. So what you get out of SCurves is a position, a velocity, and acceleration for at any point in time, along this path. So these are sort of the ideal position, velocity, and acceleration. You get those at every moment. And so on every iteration, we update the SCurves time. There's an SCurve time in there, and then it sort of advances, and produces these targets. SCurves, of course, is 3D. In Rover, we always just have the vertical part set as 0. So really, it ends up being 2D. Then we take those, for example, the desired position, which is this green dot on the line here, and we pass. Actually, we actually pass all three of these into the position controller in a single call. And then within the position controller, it looks at the vehicle's current position, compares it to the target position, and it passes that into a simple two-dimensional P controller to come up with a sort of a velocity. We call it a target velocity. So now we've got, so now we've got this position correction based target velocity. So then we come up over here to the top right here. So what we've got is two velocities now. We've got the SCurve desired velocity. This is the one that came out of the original SCurve path. We've got this velocity target, which is to correct for the position error. We add those two together to come up with a total velocity target. And then what we do is we pass this into the position controllers. Well, the position controller passes that through this velocity to acceleration, two-dimensional FF plus PID controller, right? And so obviously it compares the target velocity to the actual velocity, and that error is calculated and then turned into a velocity correction acceleration target, shown in purple here. And then we do something very similar again. We take the SCurve provided desired acceleration, that's what we call it, desired acceleration, and then the velocity correction target acceleration. So just as a small point of naming, we call the things coming out of the SCurves desired and the sort of corrections as targets. Right? Okay, so now we've got our total velocity and our total acceleration. One thing I forgot to mention actually was that this total velocity target is limited. So we don't allow it to become higher than the WP speed. So say you've got it set to 4 meters per second, it'll never be longer than 4. And also we pass it into simple avoidance as well. Simple avoidance, we have different types of avoidance in Rover and Copter. Simple avoidance is the one that just tries to stop the vehicle before it hits things. So this is not the path planning. It's not bendy ruler or Dijkstras, which try to get you around an obstacle. This is just the simpler, lower level, simple avoidance, which tries to stop the vehicle before it hits things. So we pass the velocity into that as well. And that might also shorten or even reverse the velocity target. Okay, so, right. So now we've got these, this target, this total velocity and this total acceleration, and we have to get into the attitude controller somehow. So the attitude controller in Rover there are basically two low-level controllers. There's the forward back speed controller, and then there's the turn rate controller. So for the forward back speed controller, we take just the body frame forward back component of the total velocity target. So you can imagine, you can see this orange vector here is sort of pointing, mostly up. The vehicle is pointing slightly more to the right. So, just most of this velocity target would end up getting passed into the, speed controller, but not all of it. A little bit that points back towards the line doesn't get passed in. Well, the part that is, perpendicular to the vehicle's heading does not get passed into the speed controller. Then for the turn rate controller, we take the body frame lateral component of the total acceleration target and we pass that in. But that is, of course, an acceleration. That's a lateral acceleration. That's not a turn rate. So we convert that lateral acceleration into a turn rate using the desired forward speed. So the forward back component of the speed. So that's what goes into the lower level controllers. And that's about it. There's a couple of other little things we had to do. So for example, to stop the vehicle from getting stuck, we make sure that this desired forward speed never drops too low. Yeah, you can see the little calculation here, but you just want to make sure that the vehicle doesn't stop because, at least on some vehicles, like the Ackerman steering vehicles, you can't turn unless you're also moving forward. So there's kind of a minimum speed that we apply to make sure the vehicle doesn't stop and therefore can't turn. And that's about it. Any questions?
Hey, Randy, Bill Gower.
Hey.
So how, this is on boat as well, right? This would be boat.
Yeah.
Is that correct? So how well does this handle the fact that, obviously it has airspeed and currents, and that sometimes the boat's nose may not be in the direction that it's going to be traveling. Does the SCurves handle that correctly? Like, so it can crab effectively?
It does. Yeah, Tridge brought this up as well as a concern when I first started on the SCurve project. It's totally fine. So that really is handled. It's handled just as well as it was previously. So you've got a desired velocity here. That is not, if we're trying to move back onto the path, we have a desired velocity going to the left. That doesn't necessarily mean that we point the vehicle's nose to the left. That's not, it will crab just like it does now, or like it does in 4.2.
And so, but for copter, that's not the case. For copter, it actually, your nose is always pointed in the direction you're traveling, at least from what I think.
No, not really. Where's Leonard?
Well, I guess if you had like a region of interest that you pointed it at, I guess it doesn't have to be. So I guess it doesn't have to be because
it leans the vehicle, right? It leans.
Yeah.
It will lean in the direction that it wants to go in, but still, you've got this velocity layer here, which I think takes care of it. So if you're trying to move, to the left, say for example, this vehicle is trying to move back onto the line and it's not moving back onto the line for some reason, you end up getting I-term buildup. Well, you get a P error, and then as it drifts away from the line, you get a P error, and then you get maybe I-term buildup if you've got an I-term or an I-gain set. So the desired velocity will, the desired acceleration will increase in that direction, and so the vehicle will turn harder and harder and harder, right? This this turn rate, it'll turn harder and harder back towards the line as it drifts away. Does that make sense?
Yes, thank you.
Any other questions or comments? Okay. Next is just some little overview on the logging. So some of the logging has not changed. let me first just say that this is a log from Eames, my main sponsor, and they I think were the very first people to test this on a boat. They tested it yesterday on a boogie board boat, and went okay. A couple of little problems that are written down here, but anyway, I thought it was a good opportunity to share what the logs look like, because I had to look at this log. Some parts are not changed. So for example, we still have the end tune messages are still there, and they provide you, the desired yaw and the actual yaw and the cross track error. So that's the same. And then the steering and throttle, the logging from the lower level controllers, that's also still there, unchanged. Nothing to worry about there. What's new though is we have this PIDE and PIDN. So this is the velocity controller, the output from this velocity controller. Well, inputs and outputs from that velocity controller are here. Split into the north-south frame and, well, east-west frame. And then, exactly like Copter, we've got these position controller north and position controller east logs. And if you look closely, you'll see there's a TPN and a PN. So that is the target position coming out of the SCurves, and then the actual position. That's what's stored there. Then we've got DVN, which is desired velocity north, and target velocity north. And then we've got a velocity north. So again, the desired velocity north, that's from the S-curve. The TVN is the S-curves plus the position correction. The velocity that comes from the position correction. And then finally, we've got the actual velocity. And then we've got the same thing as well for the acceleration. So the desired, target, and actual. And in this log, we can see, the vehicle was coming from the right here and then went north. Did a pretty good job of staying right on the line towards waypoint 2. Then it was actually set up to do a pivot turn though. So instead of doing a nice S-curve turn like we would have hoped for, cutting the corner, it floated, it reached 2, it tried to stop. The pivot turn controller took over, and while it was turning, the vehicle drifted with the current, and then it started on its way towards waypoint 3. And you can see here that it did not try hard enough to get back onto the path. Now, since then, they've actually done another test where they turned off the pivot controller, and it was beautiful. It was wonderful. The vehicle, cut the corner nicely, stayed right on the path. So I think, that's one possible change that we'll make, is just to maybe turn off pivot turns for boats. I don't know. Still thinking about it. And here we go. Any questions on that? Hopefully that helps people analyze S-curve logs on Rover. Okay, things that we still need to do. So the position controller, I think actually S-curves are going to be fine. The issues, if we hit any, I think are all going to be in the position controller part. So Leonard wrote the S-curves, I wrote the position controller parts. Of course, the problems are going to come from the position controller. One issue is that the position controller is working in the northeast frame, which is just like Copter. I sort of wonder if maybe we should split it, change it so that it works in body frame instead. And that might allow you to have different gains for, lateral versus forward back. We've had a few testers, of course, mostly using rovers. And so we've got gains which we think, work for all those testers, but I think it's still a bit up in the air as to whether our default gains are the best for everybody. Clearly from this log, it looks like we need an I-turn. By default, we don't have an I-turn. There's also inevitably probably going to be a couple of bugs introduced. I tested it for a long time. We had a lot of beta testing as well, but we have had some reports that bend ruler is not working quite right. So we'll need to resolve those over the coming months. Okay. If there's no questions, then I'll move on. So the next slide is just about the ongoing or the forward-looking plans for boat. I think we've made a huge amount of progress on Rover and boat. Thanks to the help of all the other devs as well. over the last couple of years. And I think we've got the navigation and control parts working really well. There are I think our next focus should be on safety and ease of use. So in particular, when I've been doing these mapping missions recently, I've really missed having like MRTL, do land start, or some way to basically get the boat to navigate through a harbor as part of RTL. We have safe RTL, so it will follow its exact path. The outgoing path, it'll use that on its way home. So that is useful, but I think I'd like to have something, and I'm sure that other users would appreciate having support for do land start, or perhaps an ability to execute the mission in reverse to get safely back to home. Object avoidance. So one of the unique problems, perhaps, of trying to do object avoidance on the water is that LiDARs just don't work very well. They tend to hit the waves and bounce back, and then you get all these false positives. So we should add support for more radars, and which bounce off the waves. We should also make sure that we've got a really robust AI camera-based object avoidance solution. So Rishab has done a bunch of work in the copter area. I'd like to extend that to so that it can recognize the kinds of obstacles that a boat would see, rocks and other boats and things like that. And we should also consider adding support for avoiding manned boats whose position has been provided by the AIS sensors.
Randy?
Yeah.
Tom Pittenger here. I think there is support, or there's a pull request by Peter to do the to treat AIS like ADSB, so it does automatic boat avoidance.
Yeah.
I think that's a lingering PR at this point.
Yeah.
Available.
Yeah, I think it's tricky. I think it's maybe. I think yeah. I think it's going to have. I think it's going to be a fair bit of work, actually. And I know that Rishab has done some work on sort of a real-time Dijkstra's or real-time A-star, and I think that's probably what we need. Bendy ruler could also work, but in my, I'm not sure. Bendy ruler might work. I'm not sure.
Am I audible?
Yes, you are.
Hi, Randy, Rishabh here. So I was actually thinking, can't we just sort of treat it as a object in the object database as of now, and then see where it goes from there, so that at least Bendy ruler can use it?
Yeah, I think that's the first, a good first step. I think that the problem is just that these man boats are very large, or they can be very large, and you don't want to come at all close to them. So, in my personal experience anyway, Bendy ruler, we've used it to get, around obstacles that are quite close to the vehicle. So, you avoid that obstacle by 1 meter or 2 meters. And I'm sure we have, configuration which can make us avoid it by much larger margins, but you certainly wouldn't want to come 10 meters within 10 meters of a man boat. You'd want to miss it by a kilometer or something like that. So I think the scale is quite different, and I'm not sure if our Bendy ruler as is going to handle that properly.
Well, I remember the Bendy ruler was actually made for planes, which is designed to be larger scale like that.
Yeah, indeed. We are missing, of course, also the velocity component, and Trish has brought this up a couple of times, in that our Bendy ruler in Copter and Rover is not using the velocity of the obstacle. We didn't have any way, we didn't have any source of like the obstacle's velocity. We didn't have any source for that before, so we didn't include that in Bendy ruler. With AIS, we do get the speed of the vehicle. So, on this slide back here, you can see it's, this ferry is moving at 3 meters per second. This boat only moves at 3 meters per second. So it's a big, we definitely need to take that into consideration when we're trying to avoid that boat. But yeah, these are all good suggestions though, I'm not saying they're not. I think it's just going to be a bit of work, but fun work. Next one is autonomous docking. So whenever I've launched my boats, there's always had to be two people, moving that boat into the water, and also when it comes back, dragging it back out of the water because they are, 45 or 50 kilograms. So it's, it's not terrible, but it's a bit of a challenge to get in and out of the water. So I think autonomous docking would be a great help. We've got that on the GSOC project list, so I'm pretty confident that'll get done over the next few months. Just another note was Peter Hall showed us a really cool demo maybe 6 months ago, maybe a year ago of some work he'd done to extract the shoreline from was it open map, something like that. Sort of think that would be interesting to integrate as well. Street view map, street map, open street map.
Yeah, open street map. Yeah, I'll get back to it. I'll get back to it.
Oh yeah, no pressure, no pressure. Okay, great. Yeah, sorry, and a few more things actually that we'd like to work on. Auto tune, that is probably our most requested feature. I find boats really easy to tune, but much easier than copters, but still, for new users in particular, it'd be great to get an auto tune feature added. Cloud integration, because boats collect up so much data and they are traveling for quite often many hours, they produce massive log files. 1 gigabyte log file is nothing. So automatic uploading of those log files would be great. Also automatic uploading of the the sonar logs, which can also be huge, would be great. And remote operation. In Japan, we have the HereLink, which has been a godsend. Gives us at least a couple kilometers of range. But with boats, again, they can go so far. You don't really want to follow them around in another boat. That kind of defeats the whole purpose. So, remote control of boats is more important than perhaps with some other vehicles. Payload integration. I guess this applies to all vehicles, but with boats, the side scan sonar. It's something that I'd like to integrate, especially using the vehicle position. So down on the bottom right here is a side scan sonar output from John Easton's, one of John Easton's posts. So, and you can see there's this little black spot, and that's actually caused because the side scan sonar's GPS was incorrect for 30 seconds or something like that. I suspect that the autopilot's GPS and position estimate is much better than what these side scan sonar GPSs can produce. So I think it'd be interesting to try and integrate the vehicle position and attitude, et cetera, into the data collected by the sonar. Maybe we could make some cool 3D maps as well. Underwater camera and microphone, I guess that's a lot like submarines. The other thing that we'd like to do is add support for more high-powered motors. So the next one on the list is the e-propulsion motors. I think the Torqeedo motors and the e-propulsion motors are the most popular electric motors on the market. So we've got Torqeedo already, at least for the low-powered Torqeedo motors. Next, I'd like to add support for the e-propulsion. They're very similar, actually. The protocol is very similar. So that should be done soon. And I think that's it. Yep, that's it. Questions, comments now?
Fantastic. Thanks so much, Randy. So questions from the floor?
I had a question. Randy, have you thought anything about the boat docking project? Are you thinking of doing it as a companion computer thing, or as a mode, as a specific rover mode that is inbuilt? Sort of like how we do precision landing in copters, or
exactly.
Do it completely off board?
So I'm thinking at the moment that it'll be very similar to precision landing. So I think that we're gonna take the AC precision landing library and turn it 90 degrees essentially, or at least use the mini EKF portion of it. Maybe it'll have to be in a new library. That my guess is that it will actually have to be in a new library. But hopefully we can.
might not
Which would-
be that possible to use. I mean, it would of course be possible, might not be that easy to reuse precision landing directly. So yeah, we'll have to see on that. But I was wondering if it would just be better to have it as a Lua script or a companion computer script or something.
Yeah, possibly. I think maybe the estimation part at least has to be in the vehicle code. So a bit like, precision landing has like two parts. It has the one part which is, where is the target? And then the next part is how do we get there? And the estimation part, I think we should, try and leverage the precision landings mini EKF. But then when it comes to, how do you dock the vehicle? How do you get the vehicle, 3 meters in front of that target and stopped and facing in the right direction? Whether that's a Lua script or a flight mode, I'm not totally certain yet. I was thinking of flight mode, but I don't think it has to be.
That makes sense. Yes.
Okay, any other questions? All right, well, thank you very much.
All right, fantastic. Thanks so much, Randy. So it was really, really good. Greatly appreciated, and really good to see how far boats have come. So we were scheduled to have another talk today, Nick's talk on ESP32, but he actually had thought it was going to be tomorrow. And so the slot at the same time was actually available tomorrow. So we've just arranged to move Nick's talk to tomorrow, which makes up a little bit for my gross overrun in my talk. And I apologize again for overrunning so far. So if we have a look at where the schedule is now, so that actually means that we've had all the talks for today. So we'd start again tomorrow morning with Ryan Beale's talk about aviation altitude handling. Ryan, are you online? You're ready for your talk in the morning? Okay, I might ping Ryan separately, just make sure that he's all ready for that. Followed by Jeff with remote ID and Leonard on advanced guidance, Bill on a heli update, and then Nick with the ESP32 update. Because I overran so far, it actually means we're not far off our planned closing time for today already. So that brings us to the end of the first session of the Dev Conference. So we'll start again tomorrow morning, Canberra time, and people have got some time this afternoon to prepare their talks for the following couple of days. And thank you to all the great speakers today. Really appreciate the talks today, and looking forward to more great talks tomorrow. Speakers, remember to put your slides, a link to your slides up on the Discuss post. That's about it. So thank you all, and we will see you all tomorrow morning, Canberra time.
Thanks, everybody.
Yeah, thank you. And Church, I just talked to Ryan Beale, and he's ready to go.
Fantastic. Okay, thanks, Tom. Great. All right, well, I'll end the recording there, and then we'll start up again tomorrow morning.
All speakers.